Sections 8.1 and 8.2 are the basis of hypothesis testing. All of Chapter 8 is about testing hypotheses to state whether or not there's enough evidence to support a claim that's being made. We're constantly confronted with people making claims about politics, claims about a product they're trying to sell, claims about a particular belief that they have, maybe a hot button topic such as abortion or gun control. It seems like folks are making claims all the time, and we need to be able to decide who has sufficient evidence to support their claim and who does not have sufficient evidence to support their claim. Perhaps we're talking about a pharmaceutical company trying to manufacture a new drug that helps with migraines, and they make the claim that people who took this drug on a daily basis had a 75% decrease in the number of migraines they had in a year. Well, we need to know how to determine if there's actually enough evidence to support that claim. So hypothesis testing is a scientific procedure, just like biologists and other scientists use the scientific method as an established protocol for conducting scientific experiments. Hypothesis testing is an established protocol for testing the validity of a claim. In statistics, a hypothesis is a claim or statement about a property of a population. We are going to restrict our hypothesis test to talking about proportions and means. There's another section, hypothesis testing on standard deviation, that we're just not going to talk about, but you could. A hypothesis test is a standard procedure for testing a claim about the property of a population. So you make a hypothesis and then you run a hypothesis test to either prove or disprove or say, hey, we don't have enough information to do either one. The main objective of the chapter is to develop the ability to conduct hypothesis tests for claims made about population proportions or population means. Examples of hypotheses that can be tested, the Genetics and IVF Institute, we've been talking about all semester, claims that the XSORT method allows couples to increase the probability of having a baby girl. Now, without any kind of procedure, roughly what's the probability of a baby being a girl? About 0.5 or 50%. The Genetics and IVF Institute claim that with their procedure, P is greater than 0.5 for having a girl. A newspaper headline may make a claim that most workers get their jobs through networking. Most would mean what proportion? Anything more than 0.5. So the claim would be that the proportion of people who get their jobs through networking is greater than 0.5. Medical researchers claim that when people with colds are treated with echinacea, the treatment has no effect. The FAA claims that the mean weight of an airline passenger, including carry-on baggage, is greater than the 185 pounds which was used 120 years ago. Not 120, there weren't planes 120 years ago. Just 20 years ago. It's got me thinking about Kitty Hawk now. I don't remember when that was. When new equipment is used to manufacture aircraft altimeters, the new altimeters are better because the variation in errors is reduced so that the readings are more consistent. What does that make you think of? The variation in errors is reduced. Which population parameter is that referring to? The standard deviation. All right, the standard deviation is reduced. When we were talking about the thermometers, which measured, we're supposed to measure 0 when put in ice water, we said actually they may measure 0.001 or 0.999, but the less variation there is among those readings, then the more precise the thermometer is. I'd rather my pilot's altimeter be precise than a thermometer in an ice bath be precise. It's important to understand that when a hypothesis, which is a claim, is stated and a hypothesis test is conducted, there are three possible outcomes. You can say there is enough evidence to support the claim, or you can say there is enough evidence to reject the claim, or sometimes you just have to say there's not enough evidence one way or the other. Not enough evidence to support or reject the claim. So our conclusion for each hypothesis test will begin, we support the claim, we reject the claim, or there's not enough evidence, but then we want to restate that in a way that it would make sense to a person who's not in a statistics class. We may say, if we find that whatever the clinic was, IVF Institute, claim is wrong, their procedure is really not working, we wouldn't just say we reject the claim. We would say there is enough evidence to suggest that this procedure does not increase the likelihood of having a baby girl. That would make sense to somebody whether you were in a statistics class or not. Note that not having enough evidence to support the claim doesn't mean that you've disproven it. If you have a medical procedure and the manufacturer, the pharmacist is claiming that the medical procedure is effective, if we reject the claim, make sure I'm saying that right. No, I'm sorry. If we say we don't have enough evidence to support the claim, that we don't have enough evidence to reject it either. Sometimes the best you can do is say, you need to go back and conduct some more research, get us some more data, because we really can't say anything about this claim. It's inconclusive. All right, so for the following claims, make a decision about the claim, use only the rare event rule and the subjective estimates to determine whether the events are likely. Let's say somebody's in Las Vegas flipping a coin. I don't know if they do that in Las Vegas or not, but this person is saying, hey, this coin is not fair. It favors heads. So to conduct an experiment, somebody flipped a coin 100 times and got 90 heads. Do you think that claim is supported, supported, rejected, or not enough information? I would say 90 out of 100 heads, that is so unlikely to occur that this person's probably right. The coin is not fair. So the conclusion is support the claim that the coin favors heads. What about this one? Movie patrons have IQ scores with a standard deviation that is less than the standard deviation of 15 for the general population. I don't know who would make that claim or what they have to gain by it, but somebody made the claim movie patrons have less deviation among their IQs than the general population does. So a study was conducted, a simple random sample of 40 movie patrons result in IQ scores with a standard deviation of 14.8. Would you say that supports their claim or rejects their claim or doesn't really give you enough information? Well, but remember the magic number 30? If it's normally distributed, which we know that IQs are, then it doesn't even matter if they use less than 30. But they've used more than 30, and we know IQs are normally distributed, so sample size is not the problem there. If the person tested 40 movie patrons and their standard deviation, sure enough, was less than the general population of 15, would we go, hey, you're right? It's really close. There's not enough evidence to support that claim. That's just not very different from 15. So that's all you could say, just not enough evidence to support that claim. If you want to go back and randomly sample another 100 people, and it turns out their standard deviation is maybe 13, then you can support your claim. But 14.8 is just not enough difference to make that claim. Components of a formal hypothesis test. Now, the things that I changed about Section 8.2 notes, I tried two things. I tried to look at the great big picture and break it down into 3 parts, because last 2 semesters the 3 parts weren't clear. The other thing I did was worked more examples earlier into the show. Instead of talking for an hour and then doing some problems, we're getting to practice each concept as we talk about it. So here are the 3 big ideas, 3 big components of a formal hypothesis test. The beginning is state the claim and identify the null and alternative hypotheses. You don't know what that means yet, and that's okay. We'll refer back to this slide. But the beginning is state the claim, identify the null and alternative hypotheses. The middle is calculate the test statistic and its p-value, compare the p-value to the significance level alpha. Well, we have talked about significance level alpha. The rest of that doesn't make any sense to me yet. Don't worry about it. The end is to state the initial conclusion. The initial conclusion will be reject or fail to reject the null hypothesis, but that only makes sense to somebody in a statistics class. Your final conclusion will be, there's enough evidence to say the IVF treatment does not increase your chances of having a baby girl, or does increase your chances of having a baby girl. But the final conclusion has to be in terms that anybody would understand, whether they had ever taken a statistics class or not. Reject the null doesn't make sense to most people. It's going to make sense to us. All right, here's what I mean when I say the beginning is state the claim and identify the null and alternative hypotheses. The null hypothesis, the symbol for the null hypothesis is H with 0 as a subscript. The word null, nothing, makes you think of 0. So the null hypothesis is H sub 0. It's a statement about that the value of a population parameter is equal to some claimed value. If we were trying to say the IVF procedure didn't work, that the proportion of girls, even with the procedure, is still 0.5, then P equals 0.5 would be our null hypothesis. The null hypothesis always says P equals something or mu equals something. It has no inequality symbols in it. We test the null hypothesis directly, and we either reject or fail to reject the null hypothesis. That'll be the only 2 things we say about the null hypothesis. We reject it or we fail to reject it. We never accept it. That'll make more sense later. The alternative hypothesis, there are 2 primary notations used for the alternative hypothesis, and unfortunately throughout this slideshow, because I did it at sometimes or several times, the alternative hypothesis, sometimes I've used H sub A being for alternative, but sometimes I used H sub 1. Either one of those is the alternative hypothesis. It's the statement that the parameter has a value that somehow differs from what you state in the null hypothesis. If your null hypothesis is P equals 0.5, then your alternative hypothesis may be P is greater than 0.5, or P is less than 0.5, or just P is not equal to 0.5. But the alternative hypothesis is never going to just be equal. It's going to be less than, greater than, or not equal to, which is what the next little bullet says. All right, We're going to practice this. Let's go through this little flow chart and then practice identifying the null and the alternative hypotheses. First, you have to identify the specific claim or hypothesis to be tested and express it in symbolic form. You may write, the claim is that P equals 0.5, or the claim may be P is greater than 0.5. But write it in symbolic form means use P for proportion or mu for mean, and then state whether someone is claiming the mean is greater than, or the mean is less than, or equal to. What is the claim? You have to know that first. Second, you give the symbolic form that must be true when the original claim is false. So, if the claim by IVF is P is greater than 0.5, what would be true if that is false? We're talking about two subsets, something and its complement. If the claim is P is greater than 0.5, what's the complement of that? P is less than or equal to 0.5. So you identify the claim, and then I like to call it the anti-claim. But I made that up. That's not in the book. You identify the claim and its complement. And then of those two expressions, you let the alternative hypothesis be the one that doesn't include an equal in any way, shape, or form, so that the alternative hypothesis just has less than, greater than, or not equal to in it. And then you let the null hypothesis be the symbolic expression that the parameter, whether it's proportion or mean, equals something. Null hypothesis is always going to have an equals in it. Alternative hypothesis is always going to have less than, greater than, or not equal to in it. Correct. No, the claim can be P is greater than, but that's not the null hypothesis. Null hypothesis always has to be equals. And you see the reasoning behind this as we go along. You may be thinking, who cares what the null is and what the alternative is? Stating your hypotheses correctly is the most important thing in determining whether there's enough evidence to support a claim or reject a claim, or whether you have to say not enough evidence one way or the other. If you don't have your hypotheses stated correctly, you're quite likely to interpret what the calculator tells you incorrectly. All right, so let's practice. This one's all typed out for us, and then I have some for us to practice. Consider the claim that the mean weight of airline passengers is at most 195 pounds. What population parameter does our claim refer to? Mean. It's not talking about a proportion. It says mean weight of airline passengers. So the claim is that mu, the mean weight, is, what does at most mean? Less than or equal to. Less than or equal to. So the claim is that mu is less than or equal to 195. The complement of that is mu is greater than 195. Which one gets to be your alternative hypothesis? The one that does not have the equal to. You never have an equal to in your alternative hypothesis. So this is going to end up being the alternative. Mu is greater than 195, and I have that typed on the next slide. The alternative hypothesis is going to be mu is greater than 195. The null hypothesis will be mu equals 195. The null hypothesis always has to say plain old equals. I don't like to think of it as dropping. We're not dropping it. We will come back to it. But for right now, do it because I said so. And then later, and then later it makes more sense why. All right? So the alternative hypothesis can never have an equals in it, not the equal sign or the equals under a less than or greater than. It must be just greater than, less than, not equal to. And the null hypothesis is always plain old equal to. Now note that the original claim was that mu was greater than, or excuse me, was that mu was less than or equal to. Well, that didn't end up being the alternative or the null. Don't worry about it yet. All we're doing now is practicing using that flow chart to identify the null and the alternative hypothesis. And then Liz will go back to, well, what happened to the less than or equal to? All right, here are some problems. We'll see if we can do the same thing as that previous example. These problems are straight out of the homework. This is exactly what the problems in the homework will say. Identify the null and alternative hypotheses, examine the given statement, and then express the null hypothesis and the alternative hypothesis in symbol form. Be sure to use the correct symbol, mu, p, or sigma for the indicated parameter. In other words, if you're talking about a proportion, use p. If you're talking about a mean, use mu. If you're talking about a standard deviation, use sigma. For every one of these, don't skip the first two steps. Before you jump in there and say what the claim, or excuse me, what the null and alternative hypotheses are, you need to write the claim and what makes it false. What is the claim here? The proportion of people aged 18 to 25 who currently use illicit drugs is equal to 0.20. How do you say that symbolically? We're talking about a proportion, not a mean or standard deviation, so we're going to use a p. And this claim is that p exactly equals 0.2. It's not greater than 0.2 or less than 0.2. It's exactly equal to 0.2. Anytime you claim something is exactly something, you're probably going to be wrong. There aren't a whole lot of things that are exactly anything. Well, that's not alternative yet. That's what makes the claim false. The claim is false if p is anything other than 0.2. You have to write those two down so that you can look at them and say which one does not have an equals in it. False if p is not equal to 0.2. So that is your alternative hypothesis. And what is your null hypothesis? P equals 0.2. The null hypothesis always has plain old equals in it. Now, in this problem, it turns out that the claim is the same as the null, and the alternative is the same as its complement. That's not always true. If it was always true, then we wouldn't write down this middle step. But that's not always true, so it's very important to write down the claim and its complement before you try to identify your hypotheses. Number 12, the majority of college students have credit cards. Are we talking about a proportion, a mean, or a standard deviation? Majority means what? Proportion is greater than 50%. More than 50% of students have credit cards. That's another way of saying that sentence. So, what's the claim? That's exactly it. P is greater than 0.5, because that's what majority means. It's not equal to 0.5. Exactly 50% wouldn't be a majority. It's got to be greater than 0.5. That's false if what? And not only less than, but also equal to. Make sure you give the whole complement. P is less than or equal to 0.5 is the complement of P is greater than 0.5. So what is your null hypothesis? Excuse me, give the alternative first. What is your alternative hypothesis? The one that doesn't have an equals in it. P is greater than 0.5. And what's the null hypothesis? Null hypothesis is easy. It's always equals. Now notice that in number 10, the claim was the null hypothesis. In number 12, the claim is the alternative hypothesis. You can't memorize it that way. You have to write down the claim and its complement, and then stick with the rule. The one without the equals anywhere in it is the alternative, and plain old equals is the null. All right, number 14 says the standard deviation of daily rainfall amounts in San Francisco is 0.66 centimeters. What's the claim? It says, it didn't say, sigma. Yeah, it says standard deviation. So sigma equals 0.66. And that's false if what? If it's anything else. P does not equal to 0.66. I wrote sigma and said P. I'm sorry. You're right, sigma. So what is the null hypothesis? It's always plain old equals. What is the alternative hypothesis? The one of these two that didn't have the equals in it. Sigma is not 0.66. It really is better to write down the alternative first. The alternative is always one of these two. The null may not be either one. Like here, the null was P equals 0.5. That wasn't the claim or the complement. And number 16 says the mean weight of plastic discarded by households in 1 week is less than 1 kilogram. What's the claim? Is it P? Mu, the mean weight. And I may have just heard you wrong, but mu is less than 1 kilogram is the claim. That's false if what? Not only greater, but greater than or equal to 0.1. So what is the alternative hypothesis? It's got to be one of these two. It's the one that doesn't have the equals. The alternative hypothesis is always, always, always either the claim or its complement, whichever one doesn't have the equals in it. So here it would be mu is less than 1. And what is the null hypothesis? Always equals.